All right, so picking up where we left off with exponentials, we're going to solve a quadratic form of an exponential, and we're going to use something called a U substitution. And all a U substitution is, it's a process that you'll use a lot, by the way, in calculus, but it's a process where you substitute a complicated value for a simpler value. So you're going to put in U, you're going to let some complicated value equal U, and then do a bunch of processes, and in the end you have to replace the complicated value back into the problem. All right, so that's a little picture that kind of describes it, but it's much more easy to see when we actually do it. In this case, I'm looking at a quadratic, almost quadratic formula. If I didn't have these x's, I would certainly have a quadratic equation. So I'm going to turn it into a simple quadratic by letting e to the x equal u. This is the u substitution part, the change out the complicated value for a simpler value. So now I have u squared minus u minus 2 equals 0. So u minus 2 times u minus 1 equals 0. And so u equals -1 and u equals 2. Now, this is the u substitution part. We didn't replace it. There are substitutions you'll use later in life where you replace something and you don't put it back in. But a u substitution means that you have to put this back in at the end. So we end up with e to the x equals -1 and e to the x equals 2. So now we can solve each x value separately. E to the x equals -1 if I take the natural log of both sides. The natural log of e to the x equals the natural log of -1. Well, natural log of e, that cancels, so I get x equals the natural log of -1. If I put that into my calculator, I'm going to get an error because, remember, the natural log function looks like this. I can't choose a -1 for the natural log. So this is actually not a correct answer. I don't really have to go to my calculator and have it tell me error. That is an extraneous solution, not a part of the function, or not a solution to the equation. In the other case, I have the natural log. E to the x equals the natural log of 2. Natural log e cancels, so I get x equals ln 2. And ln 2 is perfectly fine. This is 1, and if I choose 2, I'm going to get some positive value out of it. So let's open up our calculator and type in the natural log of 2, and I want an exact value, 0.6931. So x equals 0.6931. I like 3 decimal places, so x equals 0.693. All right, so let's have a look at a quadratic form of a log function now. We want to solve log x plus log x minus 3 equals log 28. So the first thing I want to do, since I have the same base all the way across, I want to condense the logs on the left-hand side, because then I can just get rid of the log altogether. So log x plus log x minus 3 is the same thing as log x times x minus 3 equals log 28. Now I can use properties to get rid of my logs, and I'm left with distributing x squared minus 3x equals 28. And solving for x means move the 28 to the other side and factor. So x squared minus 3x minus 28 equals 0. And if I factor, I get x minus, well, 28 and 3, let's see, 14, 7 times 4. So minus 7x plus 4 equals 0, so my x values are 7, and x equals negative 4. And now I want to look again for extraneous solutions. So if the x value on a log function, on a log graph, is positive, I'm good to go. If the x value on a log graph is negative, I'm not, because I can never choose negative 4 in my function. So I know that the extraneous solution is x equals minus 4 and that the actual solution is x equals 7. Alright, so let's expand a little bit on the idea of extraneous solutions. I want to solve the log function now of log 3x minus 4 equals 1 plus log 2x plus 3. Okay, well, if I can get my logs together on one side, I'm thinking I'm going to have to use exponentials, but maybe not. Let's see what happens if I manipulate this a little bit. If I have the log of 3x minus 4 minus the log 2x plus 3 equals 1, well, I can condense these, so I get the log of 3x minus 4 over the log of 2x plus 3 equals 1. So in this case I can't use a property to just eliminate the log values. I guess I could substitute a log value that equals 1, and if I wanted to know what that is, I could look at the graph and say, when does my graph, my log graph, equal 1? Well, alright, so I could say log of 1 equals 0, but it's not going to get pretty, so I'm just going to use a different method. I'm going to raise each to the base of 10 over the base of 10, so log base 10 of 10, that disappears. 3x minus 4 over 2x plus 3 equals 10 to the first power 10. So now, continuing on, 3x minus 4 equals 20x plus 30. So 3x, let's see, which direction do I want to go? I think I want to take 3x to the 20. So 20 take away 3x is 17x equals negative 4 take away 30, negative 34. And so x equals negative 2. Now if I plug this back into the original, so I'm going to check it now, I get log of 3 times negative 2 minus 4 equals 1 plus log 2 times negative 2 plus 3. So that's log negative 6 minus 4 is the log of negative 10. That's not possible. I'm going to keep going. Plus or equals 1 plus the log 2 times negative 2 is negative 4 plus 3 is a negative 1. Both of these logs don't exist, and so in this situation there's no solution at all. So you need to be careful to check solutions when you're dealing with exponentials and logs, because if you look at the graph, there are so many eliminated values in both cases. And so you always have to check back and make sure that you're not trying to either input or getting an output that's not part of the domain or the range, respectively.